Hello, it's Monday, the day after Easter, April 21st. Welcome to the stream. I had the day off today. I took a 4-day weekend, but yesterday we spent some time with family, my wife and I. So we I could not do my stream at the normal time. But if you are joining me today on Monday, April 21st of 2025. Really happy to see you. Glad you could get here on a weekday. Today, last time we did a bit of a longer stream, and we finished the basics of the graph coloring / register Sudoku algorithm. And we got what I think is a pretty good solution. And we're going to try to finish off chapter 3 today. So chapter 3 is all about register allocation. But there's just a few more things to be done. And we'll go along with the book. So if you don't have the book, there should be a link to the PDF, or rather a link to the main repo that has the PDF of the book. I also have the physical copy, which I love reading from this rather than the PDF, but the PDF goes a bit better on stream. So this is the book we're working on, Essentials of Compilation and Incremental Approach in Racket. And we're going off book though. We are doing it in Gleam. Gleam is a functional programming language, strongly typed for the Erlang virtual machine and for JavaScript. So right now we're using the Erlang virtual machine to do a lot of our stuff. But we're not really going much outside the boundaries of the Gleam language. So I'm assuming that our stuff will eventually be able to be compiled with JavaScript, and maybe we'll do some kind of like compiler playground type thing, which could be fun. So we last time, let me switch to the coding screen. So here's the repo. Feel free to watch it, fork it, start it, take it and go start off in your own direction. But it's Sean Cribb's Essentials of Compilation. We're on GitHub. Okay, so last time we basically made the allocate registers pass, which subsumes the assign homes pass. So if you remember, the assign homes pass was just go through and as soon as you encounter a variable, allocate a spot on the stack for it. But hi, you just stumbled over a very nerdy building a compiler stream. So welcome to the stream, Malala. Okay, so the assign homes pass, like we said, was just assigning spots on the stack. But for efficiency's sake, you want cache coherency, probably you're using less. You want to use registers as much as possible. And so we implemented register allocation with graph coloring. And that was this allocate registers pass. So I think that one thing that we could do, note the exercise here says that we should create 5 programs that exercise all aspects of the register allocation, including spilling variables to the stack. So we could do something where we have a ton of extra variables, and we use them in different spots in the functions so that they get we use up all of the registers and we get spilled onto the stack. So now we've got our 3 new passes in there. And we're going to move on to the next phase. So I don't know that maybe we'll do this creating more programs in a little bit. But I'd like to finish up patch instructions, which I think is basically the same as it was in the last chapter. And then we'll go and we'll do the prelude and conclusion, which is really interesting because that has the bit where we need to align the frame on 16-bit boundaries. So Gleam, is that C-based program like Python? No, Gleam, sorry if you missed the first few minutes, Gleam is a functional programming language. It looks a little bit like Rust, but the semantics are very much more like Erlang or Elixir or OCaml, and there's a bit stronger typing than Elixir and Erlang. So in that respect, it's closer to OCaml. Okay, so here was our allocate registers. Today we're going to go and look at the patch instructions. So it says we need to ensure that the instructions have at most one argument that is a memory access. So we have this dereference off of the base pointer register. You can't do this kind of move. You have to move into a register and then move into a memory location. So I believe we did this last time. Right, so here when we were only spilling things onto the stack and not using registers directly, we needed to, here it's moving into a memory location, immediate, that's fine. It's this one that's problematic. So we inserted, move the -8 off of the base pointer into REX and then move REX into -16. Well, now we may have register to register instructions, and we may have memory to memory instructions. So yeah, I think we should also delete trivial moves. So right, so all the 2 argument instructions that we support, move, add, and sub, if they have a deref in them, they require. Let's see if did we do this somewhere else? The patch instructions. The removing of duplicate instructions or pointless instructions. I think we did not. Okay, so we're not going. This is a note that's important to remember, but we're not going to be using RAX as a pointer, at least not yet. We're not generating that code. So what we need to do here is, I think these are fine because if they're both dereferences, so they're the the pointer type syntax, then we've already handled this from the previous chapter. But we need to do if these are the same, so it's a move that is pointless, then we need to return the empty list. Say no op move is unnecessary. I don't know how often we're going to see that sort of instruction, but it is possible to generate it, especially if 2 variables are essentially colored the same in our coloring algorithm. It does look like Rust, yeah, a little bit. Syntactically only. Bear in mind, this is a functional programming language. Rust is kind of a multi-paradigm language with a bit more leaning toward imperative, but it does look like Rust, yes. That's partly because the original compiler was built in Rust, and I think it still is. And I think I have a thing here where I need to update it. Do I need a brew upgrade Gleam? There was an issue I saw in our GitHub actions where, and you're going to go install everything else. Okay, we'll just let that go for now. There was an issue on our GitHub workflow. Yeah, so I need to update this to 1.9.0. We don't need Elixir. This became an issue because last time we upgraded Gleam standard lib, and and it's, you know, it's locked to whatever this is, but that requires a certain version of Gleam, the compiler. So we need to update that. And you're gonna upgrade everything. Okay, let's just hide the shell for now. Okay. Right, so we already handled this. Right, and so the moves between two memory locations that are the same can just simply be deleted. In their example, let's see. So they remove this line. I think let's construct this example if we don't have it already, and we'll see that we'll make sure that our pass comes out like this. I think that's a pretty sensible thing to do. So let's look at our test. Are we using the same thing here? No, let's go ahead and create this. We'll call it that. Okay, and we're gonna follow some of the same pattern here. So we're gonna do this. Okay, from list. And then, oops. There we go, there's my tuple. Start. And then we have a list of instructions. I'm sorry, this needs a block. Yeah. And we don't really care about the alignment right now. So we'll just give it a bogus 24, and we'll figure that out later. That's actually in section 3.6. Okay, so let's maybe I'll split this evenly down the middle, and we'll be able to see this side by side and transcribe. Okay. Oops. Don't save, please. That was a mistake. Move queue. Okay, and then we've got immediate of 1 into deref. The register is RBP and -8. And we've got immediate of 42 into register RCX. And then we have another move from deref RBP -8 to deref RBP -8. So that's our useless move. That should be cold when we do this. So we've got add queue. Note, I could like implement a parser for all this goop and then you know, like write it out in the text that's here on the page. But that's a whole bunch of extra work for very little effort right now. Let's copy this because there's a lot of moves in here and very little computation. So we're moving from 8 to 16. Oops. Yep. Making all the mistakes today. Okay. And then we have another move from 8 to 8, which is pointless. And then we have an add of RCX to this place on the stack. And then we have another move. Oops. We'll use that. 16. Oh, sorry, we did the add queue. This is the move queue. Okay, into RCX. If you're new to the stream, welcome. I hope that this is going to be informative for you, but I also recognize that we are well into the book, and so you might be missing some context. I'll do what I can to explain that as we go, but there's just going to be some stuff that you missed, unfortunately. You know, pulling down the PDF, reading, finding out where we are will be helpful. Sorry, that's 8. In catching you up. Also, welcome. Thank you for coming. All right. And we have finally another ad. Register RCX. This would be so much more tedious without autocomplete. And I think I'll want to clean some of that up some more. Okay, and then finally we have a jump conclusion. Okay, so let's go up here. Let's import. Actually, we can probably do it from here. Unqualify that. And unqualify that. Okay. Yes, I hear you, Bianca. My cat was yapping at me. Okay, so this is the input program here in this left column. What we want is the output program. So I'm going to copy and modify. I think that'll be the most straightforward way to do this. So we'll do let p2 is this. Now this should already fail, but we're going to go through and make sure that we get the right set of instructions. So those two are fine. This gets removed. Okay, so then we have this move will get removed. So we're gonna let's move it up. And this is going to move into RAX. Okay. And then it's going to move from RAX into 16. Yep. Okay. And then we'll add RCX to -8. 16 to RCX, -Q RCX. Yeah, so that's our transformed program from this to this. So it removed some unnecessary moves, and it also made sure that any moves from a memory location were into a register, and from a register into a memory location, no memory to memory. Register to register is fine, just no memory to memory, and that's what this stuff is that we did last time, right? It is noting that there are 2 stack locations here, basically pointers, and replacing them with moves into REX, and then using REX as an argument into the next instruction. Okay. So let's see if our test passed. No, homebrew's not done yet. All right. Okay, so that's just complaining that we didn't use call queue, and that's fine. So this test just passed, so we can be certain that our patch instructions basically modified only 1 line in there. That's pretty good. So I'm going to make a real quick commit here, and this is chapter 3.5, update patch instructions. Okay, we'll push to main. And then, okay, we're done. What version do you have? I can't even type. Oh, it's -V. Okay, -V. Okay, we're on 1.10. Woo. Okay, let's update our versions. That did not change anything. So let's update to 1.10. Gleam moves fast. Okay. Update GitHub Actions workflow to Gleam 1.10. Okay. And now it should no longer be giving me a red check mark or a red X on the GitHub page. Okay, let's go back to the book. So the next step is generating the prelude and conclusion. And if I scroll down a little bit, this is the sequence of phases that we have in our compiler and all the intermediate languages. So we're starting with this Lisp-like language with variables and integers. And then we go through several phases of that. It goes to a modified version of that. And then this phase turns it into a C-like language with variables. That gets the select instructions, turns it into x86 assembly-like language with variables. And we do a couple phases. And then I actually have a difference here in that there's this transformation from allocate registers for my language produces, or my compiler produces int. So just integers and registers and stack locations. Whereas the version in the book still has variables. I don't quite understand why yet. This phase to me seems like a very natural transformation from removing variables, because you're giving those variables spots on the stack or in registers, right? So you don't need to keep the variables around after this phase. That said, maybe there's something we haven't encountered yet, and we'll revise that later. And then we do patch instructions, and so we're about to do prelude and conclusion. We already have this from the previous chapter, and we need to adjust it. So let's read what they have to say. Okay, so this pass generates the prelude and conclusion instructions to satisfy x86 calling conventions. So that is which registers are saved, where is the return value, and so forth. So with the register allocator, the callee save registers used by the register allocator must be saved in the prelude and restored in the conclusion. So that means if we're allocating a register, we need to track that we're allocating it. And that's going to be an interesting change to what we did in allocate registers. So we'll have to go there first. So they're saying, and bear in mind, like Gleam is an immutable functional programming language. Racket is not. Racket has global variables. Racket has mutable data structures. Ours are always copying. There may be sharing underneath in the implementation, but from a semantic perspective, they're always copied. So we don't have the opportunity to kind of have a mutate bit on our program struct. We can't treat it as mutable. We have to reconstruct it or copy modify type thing. So regardless, we need to add, and I think that here the challenge is we've been putting some of this stuff on blocks. And I think that we need to put this on blocks as well for now. We'll see. There's, all of these things that change the structure of the type, the variant constructor, cause rippling effects throughout. So we need to be careful how we use that. Okay, so the call save registers are, there's like 6 of them, I believe, 6 or 8 of them. So whichever ones we allocate, we need to record. We'll probably just put it in a list, or maybe we'll use a set data structure. And then it says the prelude and conclusion pass can then access this information to decide which call save registers need to be saved and restored. Okay. And then when calculating the amount to adjust the RSP in the prelude, this is about aligning the frame. Make sure to take into account the space used for saving the call save registers. Also remember that the frame needs to be a multiple of 16 bytes. We recommend using the following equation for the amount A to subtract from RSP. So let S be the number of stack locations used by civil variables. So we need to track not just the number of registers we allocated, but also the number of stack locations. Okay, and let C be the number of call save registers. So maybe what we could do, we need to know which ones, right? Right, so let's look at our allocate registers algorithm again. This is basically, we're expecting here at this point that there's only one block. That won't be the case in the next chapter. But when we're at this point, we assume there's one block, and that represents our function that we are compiling, right? And then we are allocating registers for each block. That's how our thing works. So inside the allocate registers, we are extracting the conflicts. The conflicts is a graph that we constructed in the previous phase of all the variables that are alive at the same time. So it's like if you have variable A and variable B, if they are both alive at the same time, there'll be a conflict between them, which means they can't be spilled into the same place on the stack or allocated to the same register. But if they have different lifetimes, here's that rest thing again. But if they have different lifetimes that are not overlapping, then you can have them share a register. And then the graph coloring algorithm does that. So yeah, okay. So what we've got here, this extract assignments takes a list of, okay, so color graph, right, this does the unfold. I had to implement this from scratch last time, this unfold function. Okay, so it does one step, taking the graph, and it picks a vertex with the high saturation, right? So that's what this function does. And then if it gets one, if it finds a vertex, then it colors it, and yeah, and then updates everything. So what we're getting out of here is a list What is the definition of this node? So we have location and assignment. And this integer is maps to a location. So, 0 through 10 are registers that that we can put our variables in. And if we use more than 10, more than 11 in this case, we use more than 11, then we'll be spilling onto the stack. So I think that what we could do is, so this is giving, is mapping a location. Okay, so this is, when it says x86, that's this base file where we're sharing things. So this is giving us a dictionary of locations. So that could be a register, it could be a deref, but it's probably either a register or a variable, and then it's mapping it to what the argument is. But I think that we probably want to let's split this out. Let's call it colors, and we'll do this. And let's unpipe that because we don't need a pipe there. Okay, so those are the colors, and then we're gonna do extract assignments on the conflicts. But then we also, I'm sorry, not the conflicts, the colors. We also need to get we need to create a set let's say it's like this assignments. Actually, we just need the args, right? Okay, so let's say this is the used callee. This would only matter for variables that need, or registers that need to be saved by the callee. And I'm going to have to scroll back and find that. Or maybe I'll flip through the physical book, because I think it's going to be a little bit quicker for me than scanning through the PDF. The other thing is I have a cheat sheet that's like what are the caller and callee saved registers. Okay. Okay. The callee save registers are RSP, RBP, RBX, R12, R13, R14, and R15. The caller save registers are the other set in this calling convention. So in order to get this used callee, what we want to do is we'll just make a variable here. And let's take the assignments. And maybe I didn't need to unpipe that. Does it have an inline? Oops. Inline the variable. Okay. Convert to pipe. Convert to pipe. Woohoo! There we go. Okay. So what we're going to do here is we're going to collect the so we'll get the values and then we're going to filter And I think that I'm going to make a function here in x86 base. Two of them is callee saved. And this is going to take a register and return a bool. Oh, not match, case. What language am I in? All right, add missing patterns. Okay, so we know that, I'm going to move this up. So we know that RSP is one of them. We know that RBP is one. And RBX, I'll never understand this convention. One of those things that is like accreted over time. Maybe originally it was thought out, and then it's like, oh, well, we have space for a bunch more registers, so let's just decide which ones are callee saved and which ones are caller saved. Okay, so then I'm going to here. I'm going to do this and put a pipe in there, and these are going to be true. Oops, true. And then the rest are going to be false, so we'll just use an underscore pattern. Okay, so that's is callee saved. And let's make another one, which is, because this is going to be useful later as well, caller saved. Okay, and then we'll do something similar here, and I'm going to simplify this case reg based on what they have in the book. So RAX or RBP or oops, wrong one. RCX, RDX, RSI, RDI, R8, R9, R10, R11, true, and anything else is false. There's probably a simpler way to do that, but this is fine. So we're going to list filter to with our x86 dot is callee saved. Okay. Except this is an arg, not a register. Okay, so we're gonna have to do more with this. So case of arg, and if it's this is x86 int, it's a register, reg, then we want to do reg, otherwise false. Okay, so I had to make another step here because this argument type is either immediate, register, or deref. Okay. Okay, so that collects the used callee registers. We also need to find out how many stack locations we've used. So I think I'll do another one. We'll call it stack size. And we're going to say this is assignments. And we're getting the values again. And then we're going to do we're going to map. Would filter map do it? We can do that. What I want to do is just get the ones that are derefs. So here, this is going to be an arg again, and if it's a deref, we don't care about the register, and then let's say this is the offset, then we want to return OK offset, and anything else we return error nil. Okay. And then I think we want to do reduce. Is there a min function? Oh, it's not going to be in dash. I'm sorry. We're going to need the browser because there's max. Max, but no min. That's really weird. Okay, so you have to give it a compare function. That's fine. Let's look at the order library. We can negate. Yeah, let's do that. Okay, so we're going to do another pipe here, list.max, and we're going to give, this is A and B, and we're going to do order.negate of int.compare, and this is Gleam int, because I need to disambiguate that, A, B, and yeah, I've already got it there. Okay, so we need to import Gleam order. Oh, had it in there twice. Okay. So what did I just do? Oh, I put this on the wrong thing. Okay, that's the problem. So that'll actually give us the minimum. Right, okay, there we go. So that'll give us the minimum. I wonder if we could factor this out. It does, Gleam does let you do wildcard spots, but I don't, yeah, it doesn't let you sugar that. More than one argument hole. Yeah, okay, so we'll back that out. That's a shame. Okay, so this gives us the right, okay. So I get the list of int. Oh, so if there's no maximum, you get error nil. All right, so I think that what we want to do is provide a default for a result. update. Right, okay, so we want result, we want unwrap, which is nice that that's there. Unwrap. So if the stack size I'm going to also map the result there because we want the stack size to be positive here. This is an offset. We'll say offset negate it. We can do int dot negate there. That's Gleam int because we've got to import that. And divide it by 8. Does that not work? Yeah, okay. It it doesn't like double sugaring that, so we'll do it down here. Okay, so what we're trying to get is the number of variables on the stack, right? Not the offset or the maximum, bytes subtracted from RSP. We're just trying to get this. So what we're going to do is we're going to put stack size here, right? Because that was what that was before. Did I not unwrap it? Oh, divide returns a result. Well, let's pick a different function then. Or we can do another unwrap. Okay. That was a very roundabout way. Honestly, it's fine. I got a little bit happy with the piping here, and I could have probably simplified that. I could do it up here. Let's see about that. Let's do negative offset divided by 8. And then we don't care about, we just use int.compare. Okay, that's much simpler, and I can understand that better now. Okay, so this is, we're taking the offset and we're using an infallible division there, rather than this one that, could return. Now, interestingly, if you divide by 0 in Gleam, it turns out to be 0. Not infinity, not error. So that's something to think about. But in this case, we're dividing by 8, a constant integer. So we don't need to worry about that. Okay, so this should give us the stack size. And now we need to capture this used callee. So in the block type here, note we have the frame size. Why don't I rename this? You're not going to allow me to rename. Okay, so let's do used callee. And what I want to do here is also turn this into a set from list. Okay, so this will be a set.set. What does this say? Of args. Why don't we change this to filter map and say this is error nil, and this is, we'll put this here. Okay, register. So then it's registers. Okay, that cannot be used in a guard. So we need another case here. Okay, that's not too bad. I don't like it, but it's not too bad. You can't put this into the guard because it's not a guard safe expression. Okay, so even though it could probably be technically inlined by the compiler, I don't know. Okay, so now we get actual registers. Why does that still think it's arg? I think I need to restart register. Oh, we've got register. Okay, we're going to import Gleam set. Okay, and we should be getting errors down here, but I'm not seeing it. Yeah, now it's complaining. Incorrect error D. Okay, so this needs to be, oops. Not assign homes, thank you. Restart the language server. It did not register that we changed this. It did in the other file. Okay. Okay, nothing special there. Okay, honestly, the compiler will tell us if it doesn't work. Okay, the problem here, incorrect arity. Oh, assign homes. Forget assign homes. Honestly, let's get rid of assign homes. Because we're not going to use that anymore. So let's remove... So this, we in the last time we didn't do this, so we need to fix this bit. We didn't do the full pass, right? So after select instructions, let me look at the graph real quick. sequence of phases. Okay, so after select instructions, we need uncover live. We're getting rid of assign homes. We need uncover live. We need build interference. Oops. Build interference. And we need allocate registers. And I think it's not going to work until I get rid of that assign homes, because I really don't want to update that right now. So build interference. And we're going to do allocate registers. Okay, and we're just going to okay, so now that that doesn't reference it, what errors do we have? Yeah, error. And same there. Thank you with the did you mean? That was helpful. Okay, so this one, we'll come back to this when we get here, but I just need to make the types pass. Yeah. We'll just make an empty set again. And I think that that resolves that. What else do we got? Okay, so patch instructions needs block.usedCallee to pass that along. And honestly, what we should be doing is block like so. Let's do it like this. And then we can unpipe that. Nope. It'll let you pipe, but it doesn't want you to unpipe. Okay, so that's a little bit better. This spread syntax is kind of like JavaScript. It's also used for lists, but when you're updating a struct, and you only want to set a few fields, you can basically use this as a copy, and then it'll apply the updates to that copy. Okay. What now? Right, so now we don't need this. And for funsies, we can run our program and see what happens. Okay, so we've got a problem still in the test. This does not surprise me. Let's just ignore it. Hold on. Okay, so this is the result. This is a bit where, and this should probably fail. But we need to make sure the types line up. I'm just going to put empty ones in there. We'll come back and fix those later. This is the thing I was worried about earlier, is that, oh, I added a new field to this, so it's going to require updating everywhere, and that's not real pleasant, but okay. Where else? Patch instructions. Okay, now we just have 2 warnings. I think we can ignore those for now. Let's see what happens when we run it. Okay, so we did our little program. Our program is, this is our LVAR program. It's let y of let x is 20, and then add x to let x of 22. And returning x. So, like, not very interesting, but if we look here, interestingly, our frame size is 0, so it's adding 0 to RSP. Not quite correct. We may want to omit that instruction if the frame size is 0. But we did assign, we do have some call save registers in use here, so we're gonna have to deal with those. But you can see we move 20 into RDX, 22 into RCX, we add the 2 together, move RDX to RAX, which is where the result goes, and then we jump to conclusion, and so forth. So, okay, what were the warnings? Oh, let's just remove call queue, we don't care. Get rid of that warning. Any other warning? Okay, yeah, so when we redid that, I got rid of the order negate. Oops. So we don't need that. Okay. So now we should have some failures in our test, because we are going to get out of the allocate registers phase a list of callees and the stack size, right? That's problematic that we did not get a failure in this test. So I would expect this. Let's list the callee save registers that are in use here. And this is interesting in that we probably need to have RSP and RBP in it every time, because we are going to be manipulating those. But we didn't use any of those registers. In this example. So I think what we need to do in here is we're going to union that with a set from list of RBP and RSP. because we're always doing those. The thing is, though, technically, we don't have to restore RSP, right? Because that's the stack pointer. So I think that we just want RBP in there. Let's go down a little bit farther and see what they do. Okay, so here's an example. Give me a second. So they're using RBX. RCX is caller saved. They use RBP. So maybe we need to but hold on. Okay, so in their prelude and conclusion, they always push RBP to save it. They move the current stack pointer into that. And then they push any callee save registers. So in this case, RBX, right? And then there's the sub queue to align the frame for RSP. Okay. Okay, so now we're actually getting an error. We should get set from list RBP. Yeah. Okay, now it's passing. So this is no longer really the frame size. This is more number of stack locations used. So I kind of want to rename this. Let's call it stack vars. And I don't think that's going to require any changes anywhere. Okay, so we need to do. We're gonna redo this anyway. That's fine. Yeah. So let's go in here and look at what they are saying. We're not going to do the challenge today, I don't think. We're just going to finish up this section 3.6. Okay. So we got the used callee. The store is a set of callee saves registers that were assigned to variables. Okay, so RBP doesn't technically go into that. So I think that this is actually correct the way it was before. And we only need to be concerned with yeah, so let's get rid of that. We only need to be concerned with the ones that were actually assigned two variables. Okay. Prelude and conclusion pass can access this information to decide which callee save registers need to be saved and restored. Okay, so let's go in here. Right, so here's so we need to make a function. This is like generate main, generate conclusion. Okay, so we need to make a function. This is their align function, and that's going to take stack vars is an int, and then frame needs to be a multiple of 16 bytes. Okay. So align, what does align do? Rounds a number up to the nearest 16 bytes. So we'll say it's bytes. All right, it's simple math, Sean. All right, let's look at the standard library. So I'm thinking what we do here is we do like an integer division and modulo. Okay, so we'll do that. If it's 0, then we just return bytes. If it's anything else, then we can use truncated. So this would be bytes divided by 16. Right? So that would truncate it. Yeah, and we need to put more brackets around here. Probably don't need that since division binds more tightly. So we're truncating. So let's say the input is 24. So we divide by 16, we get 1, but we want to align to 32, right? We want to round up to the nearest multiple of 16. So we divide by 16, we add 1, which gives us the next one up, and then we multiply by 16 again. A little bit funky, but I think that'll give us what we want. So the other challenge here is that I think we want right, so this is what we want to do here is get the alignment, not this. So we need to unfortunately do this in both of these. We need to do it on the outside. So I think that what we're going to do is we're going to make a new function here. And then we need to get the save registers, and that needs to be consistent across these because we want to do it forward in one and then backward in the other, right? So we're pushing onto the stack and then we're popping off of the stack. And this is probably just going to be okay, we'll make the function there. And then we need to pass both of these in. So this needs alignment and saved registers. And then it won't be something that we have to recompute and might, like, for example, the registers might come out in a different order because it's a dictionary. I wouldn't think that would happen, but it's possible. So here, this is going to take alignment is going to be an int, and then registers is going to be a list of registers, right? And we'll do the same for the conclusion. And we're going to have to do some other business here that's a little bit less fun, but we'll come back to that. So let's make the compute frame alignment function. So it's going to be program. This is going to return an integer. So here's where we're going to do that formula they gave us. So we're going to say we need to get the start block, just like we do down here, because that's what our function is. Okay, so we're going to say align of 8 times start block dot stack vars, right? Let's copy this. Plus 8 times set dot size, set dot size, yeah, of start block dot used callees. Okay. And then, so so we need to subtract that. It's kind of a messy way to say that, but I think that this does exactly what that formula is saying. So I think it's okay. We could factor this out into a variable. Okay, that's a little bit cleaner. So I think the interesting thing here is that, yeah, okay, so if there are no stack variables and there are no save registers, then this should be 0. If there's one save register and no stack variables, then what we should get is this should return 16, and this will subtract 8, and so we'll get 8, right? I think so. That makes sense to me. Okay, so now let's implement this. I have a feeling that when we do this, when we do this later, we're going to have some issues with this, because I keep doing like, give me the start function. Okay, so we're going to do set to list of start block dot used callee. Okay, so that gives us a list of registers, and that's in consistent order. So now in main, it's just complaining those aren't used. So what we can do is this should be alignment and we can omit that instruction if it's 0. We can leave it in too, but so now after we push RBP, this is the part that bugs me, is that technically RBP is saved. Even though, so the alignment's going to be off by 8. I think it's worth looking at some of the examples earlier in the earlier in the book. So nope, that was the end of that. Right, so here RBP is a yeah, I don't know why this is 16. I guess it's because we count RBP. Okay, so if there's 0 save registers, Yeah, okay, maybe what we need to do is +1 because we're always saving RBP. But we're not counting it in there because it's not necessarily referenced inside that function. And like RSP is implicit because of the alignment and popping. So like when you enter or when you finish the conclusion block, it should be back at the spot where it started when it entered main, right? So let me think about this. So let's say we have 0 call save registers used in our function. That would mean this is the size of this is 0. We add 1. So if we're not using any registers, we're not using any stack variables. We haven't spilled into the stack. So this will be 0. So we have 8, which aligns to 16. So we should get 16. And then we subtract 8. So that gives us 8. Yeah, I don't know why this is sub Q16 here. I don't know that that's correct. Is that because... Yeah, that's surely not right. All right, we're going to go back to this. Okay, let's say we use all the save registers. Or let's say we use 1. So that would give us, this would be 16, which would align to 16. And then we would subtract 8 again. No, we would subtract 16, so it would be 0. That sounds right, because this would be 2. So honestly, I think that we'll never have a sub Q16. Nearest 16 bytes. Okay, so the reason we subtract 8C in this equation is that the prelude uses push Q to save each of the call save registers, right? And push Q subtracts 8 from the RSP. Right, so that's just reserving space for the one spilled variable. Oh, okay. So they're using fewer colors. We're using all of the colors possible in our graph. All right. Okay, so we're going to have to do some stuff here. I think that this is fine. Add 1 because we always save our BP. Okay. So let's look at generate main here. So what I want to do is we're going to do these 2 instructions. Right, because the base pointer is where I think we need to push all of them, and then we move RSP into RBP. Yeah. Okay, so we're gonna say let pushes, and we're going to take right, and then we're going to list map that because we want to push RBP first, right? We're going to list map that into x86 push Q, x86 register of R. And then we're going to say aligner is if alignment is 0, then we do an empty list. Hello, come on. If it's anything else, then what we want to do is this subq instruction. Okay, so now our instructions are going to be okay, well, we'll do list.concat. Is there a concat function on list? I think there is. List append. Right, so, okay. We'll append pushes, and this will be that. And then we'll do instructions. So those, oh, yeah, the problem was that was not the same type, so fix that. Okay, so those are our instructions, and then what we'll do on the conclusion is we'll do something similar. So let me hide the shell here for a second. Okay, so for the conclusion, we're going to, we'll make pops, and that's going to be we'll map again, and this is going to be a pipeline, but in this case we need to reverse it, so we'll reverse it at the end. Pop Q register R. Okay. Reverse. So there it's in backwards order. So the next thing that we need to do is we need to do the aligner again. So we'll copy this, except this time it's going to be add Q instead of subtract Q. Okay. And so we'll do the aligner. Append the pops. And then we'll add the ret Q instruction. And those will be the instructions for okay, so interestingly, we no longer need that start block because we're generating the conclusion, right? And we no longer need the actual program. And I think the same thing is up here. That's kind of nice. So they're really only dependent on what the save registers and the frame alignment are. Okay. That's good. Whew. Okay, so I know our tests are going to fail, as they should at this point. But let's do Gleam run and see what happens. Okay. So, yeah. So we push. Now, one thing we missed is we did not save RSP into the base pointer. So that's a thing we need to fix in here. Yep. Otherwise, that looks pretty good. Okay. So after the pushes, then we insert a move from RSP into RBP. And then down here, do we need to do that move again? But backwards. I don't think we do. No. We just shift the frame down, pop off the save variables, pop off RBP, and then you return. So I think that this should be correct now. Okay, let's look at the conclusion. The main. We push RBP. We move RSP into RBP. We subtract 8 to get frame alignment on RSP because we have one thing pushed, right? And then we jump into start. And this is using all variables, and it's moving into REX at the end and jumps to conclusion. We realign the frame back down, we pop RBP off, and we return. So RBP was saved and restored, the alignment was retained, and so on. Okay. So now let's run the test and see what happens. And yeah, that should fail. So the generate prelude and conclusion test. Let's look at that. Okay, so part of the problem here is that we did not really so in this case, there are no callee save registers in use here, but we have everything on the stack. And we're using 1, 2, 3 slots on the stack. So those are 3 stack variables, right? Right, so this should give us, so 3 stack variables plus RBP. We have no Kali save variables, so that should give us 32. It should round up to 32. I think something might be wrong in our computation here, but let's see. Let's see what we get. Well, yeah, we had that wrong. Let's run the test again. Okay, so we're expecting this. That was the left-hand side. The conclusion is the same. For main, we push RBP, move RSP into RBP, subtract 24. That's the same. Oh, the issue is probably that this says 24 and should be 3. Yeah, okay. So our calculation is actually doing that correctly. We have 3 variables plus RBP. Yeah, I think that's correct. That actually should be 4 though. So it should be 32. Except that when we push, we're already subtracting the 8. So yeah, okay. All right. Let's make a commit here. Let's look what we got different. So we deleted, let's go ahead and remove now unused assign homes pass. Okay. So now okay, so this is chapter 3.6, I believe. That's what we're in, right? 3.6. Yeah, we're not going to do the move biasing. This is really interesting, and I suggest you read it because it's another graph. But what it can do is you can cut down on some moves. I think if 2 variables end up being assigned to the same color. Yeah, so it's a pretty neat technique. All right, so going up here, so we added that. All right, and we added this. We adjusted this to not be frame size but stack vars, and used Kali. Okay. And then we are tracking this stuff in allocate registers without changing the coloring algorithm. And then we're generating prelude and conclusion. And then we've got a little type fix there. And then we've readjusted the main entry point for this. And that was just, those are just some more type fixes. And fixing those tests. And then fixing patch instructions test. Okay. update, generate prelude and conclusion. Callie saved registers and alignment. Okay, so let's push those up. And I think this is 15 minutes early, but I think this is a good place to stop. For next time, we may consider doing the challenge about move biasing. The other thing that we might do is we might just go on to chapter 4, which is about Booleans and conditionals. Super interesting stuff there. It's going to put a lot of pressure on our current design to adapt, which should be really interesting. So thank you for joining me on this Monday stream. I will see you hopefully on this coming Sunday, and we'll continue building our compiler. Thank you so much.